Welcome to the deep dive, where we cut through the noise, extract the essential knowledge, and help you become instantly well-informed. Today, we're doing something a little different, actually. We're launching a special series. It's designed specifically for those of you gearing up for the CSWIP 3.1 Welding Inspector exam. Our mission really is to navigate some leading multiple-choice questions, the kind you'll see on the new CSWIP exam format. We want to give you not just the answers, but crucially, the understanding behind them. Think of this as, well, your shortcut to confidence, helping you really master the material.
That's precisely right. And these questions, they're specifically crafted to test your core knowledge and, maybe more importantly, your ability to apply it, in real-world scenarios.
Right.
So we'll definitely go beyond just identifying the correct option.
Yeah.
Our goal is to help you grasp the why behind each answer, which is absolutely key for true mastery in this field.
Okay.
We'll present each question, and then we'll really discuss the options thoroughly, just like you'd need to do in the exam. Break down the details of each choice.
Okay, sounds good. So let's put on our inspector's hat, shall we, and dive into our first foundational challenge, understanding the regulatory landscape. This one deals with relevant standards. Here it is. The European Standard for Non-Destructive Examination, NDE, of fusion welds by visual examination is A, EN 15614, B, EN 2560, EN 9606, DEN 1C637.
Okay, so this is a critical piece of information for anyone stepping into a welding inspection role. Visual examination, VT, as it's often called, it's not just the first NDE method used, it's often one of the most important. It's, the inspector's eyes that catch so many potential issues right there at the source, helps prevent bigger problems down the line. So for this specific question, the correct answer is D, EN 19637.
Okay, D.
Yeah. This European standard, its title is pretty clear, Non-Destructive Testing of Welds. Visual testing of fusion welded joints. It outlines everything, the specific methods, the conditions, the requirements for performing visual inspections.
Oh, okay.
Things like optimal lighting conditions, even the qualifications needed for the personnel doing the inspection.
Yeah.
It really is the blueprint for how to properly look at a weld and assess its surface integrity.
Got it.
Now, understanding why the other options are incorrect for this question is just as crucial, both for the exam and, for your work later. If we kind of zoom out a bit, look at the bigger picture of quality control and welding, each of these standards plays a vital but distinct role.
Right.
So EN 15614, that refers to Welding Procedure Qualification. Think of this like your a recipe book for getting perfect welds.
Okay, the recipe.
Exactly. It dictates how a welding procedure specification, a WPS, is developed and qualified. It's all about proving that a specific welding process, using particular materials and parameters, can consistently produce sound welds that meet the required quality levels. So it's about the method, the recipe, not the visual check afterwards.
Makes sense.
Then you've got EN 2560. This one relates specifically to covered electrodes for manual metal arc welding, stick welding consumables. This standard specifies classification requirements for those electrodes. So if 15614 is the recipe,
then 2560 is the ingredients.
You got it. Exactly. Ensures you have the right ingredients. Vital for selecting consumables, but again, doesn't cover the visual examination method itself.
Okay.
And finally, EN 9606. This is about welder qualification testing. It sets out the requirements for qualifying the welders themselves for fusion welding of steels. It ensures the person doing the welding.
The chef.
Precisely, the chef in our analogy. It ensures they have the necessary skills, the competency to follow that qualified welding procedure. So it's about the individual's ability, not the visual inspection process.
That's a really fantastic breakdown. It paints such a clear picture of their individual roles, but as you kind of hinted, they don't just operate in isolation, do they? They often, connect.
They absolutely do.
So let's dig into those relationships with our next question. Building on that understanding, let's see how these pieces fit together. With reference to the previous question, two of the standards are closely linked to each other. Which are they? A and B. EN 15614 and EN 2560. B, D, and C. EN 2560 and EN 1606. EN 15606, D, and D. EN 15614 and EN 1607.
This question really gets to the heart of how quality assurance works in welding. It's all connected.
Yeah.
When you consider that whole quality control framework, the correct answer here is CA and C. That's EN 15642 and EN 9606.
Okay, procedure and welder qualification.
Exactly. What's really fascinating here is that direct, almost symbiotic relationship between qualifying the welding procedure, EN 15614, and qualifying the welder, EN 9606, to actually carry out that procedure.
Right.
Let's go back to the analogy, EN 15612. That establishes the how-to, the proven method, the recipe for making a sound weld. It ensures that if you follow these specific steps with these materials, you can achieve the quality you need. But, well, a great recipe is pretty useless if the chef isn't competent, right? That's where EN 9606 comes in. It makes sure the person doing the welding has the skills, the dexterity, the knowledge to follow that how-to guide effectively. You need a proven method, and you need a skilled individual to apply it consistently. They really are, like you said, two sides of the same coin when it comes to ensuring weld integrity and overall quality.
The recipe and the chef.
Spot on. A qualified procedure proves the process works. A qualified welder proves they can do the process. Both are absolutely essential for reliable welds, and you'll see them referenced together all the time in project specs.
That's a perfect way to think about it. So for someone prepping for the exam, it's not just memorizing numbers, it's truly getting how they function together as a system. That's a key takeaway. Okay, let's shift gears now to a very practical scenario, something any visual inspector will definitely face, figuring out how serious different weld flaws are. When visually inspecting the face of a finished weld, which of the following flaws would be considered the most serious? A, excess weld metal height. B, start porosity.C, spatter.D, arc strikes.
Right. This is a crucial distinction. It directly impacts your decision, accept or reject the weld. While all of these are technically flaws or discontinuities, their severity varies hugely, and that often affects the structural integrity in very different ways. The most serious flaw listed here, without a doubt, is D, arc strikes.
Arc strikes, okay.
Let's quickly touch on the others and why they're generally seen as less severe, at least from a structural viewpoint.
Yeah.
Excess weld metal height. That just means the weld bead is too tall, goes over the reinforcement limit specified. It's mostly a geometric thing.
Right, just the shape.
Yeah. I mean, it can sometimes act as a stress raiser if the transition is really abrupt or cause fit-up problems later, but often it's relatively minor. It can be accepted within certain limits or easily fixed by grinding. It doesn't usually compromise the basic integrity of the joint itself.
Okay.
Then start porosity. This is just localized gas pockets, usually right at the very beginning of a weld run. Now, porosity in general isn't great, but start porosity is often isolated. And it usually happens in a spot that's going to be welded over again or maybe even cut off.
Ah, I see.
So if it's minimal and localized, its impact on the overall structural integrity is often pretty low. It's a volumetric flaw, yes, but its limited extent usually makes it less critical than, say, other types of porosity or more dangerous surface flaws like cracks.
Gotcha. And spatter, that seems pretty minor.
It generally is. Spatters, those are just small, molten metal droplets that have solidified and stuck to the base material next to the weld. They're largely cosmetic.
Right. Just looks messy.
Exactly. They can be unsightly, sometimes interfere with painting or coating, but they rarely, if ever, impact the structural integrity of the weld or the parent material. Usually, they're just removed by chipping or grinding, or sometimes just left alone if they don't get in the way of anything.
Okay. So if those other flaws are generally less severe, maybe easier to fix, what makes arc strikes so critical? Why the high level of concern? It sounds like maybe just a small mark, but you're saying the implications are big.
They really are.
Yeah.
And you're right. It is a common misunderstanding sometimes. People outside inspection might think, oh, it's just a little scorch mark, grind it off, no big deal.
Yeah.
But that thinking is dangerous. Which leads us perfectly into our next question, really digging into the why behind the seriousness of arc strikes.
With reference to the previous question and the correct answer, why is it considered so? A, it's a stress raiser. B, it's a hard spot. C, it's lack of fusion. D, it's a volumetric defect.
Okay, so when we talk about arc strikes, their seriousness, it really comes down to what they fundamentally do to the material itself, not just how they look on the surface. And the answer, the core reason is B, it's a hard spot. This is where the metallurgy comes in.
A hard spot. Okay, explain that.
Right. So when that arc hits the base metal accidentally, it creates intense localized heat. Melts a tiny spot, just like in the weld. But here's the difference. That tiny hot spot is surrounded by loads of cold base metal.
Acting like a heat sink.
Exactly. A massive heat sink. It pulls the heat away incredibly fast. An uncontrolled quench, basically. Now, for many steels, especially carbon and low alloy steels, this super fast cooling, it doesn't let the metal form its normal, tough structure. Instead, it forces it to transform into something else. Often, it's martensite.
Martensite, I've heard of that. Very hard.
Extremely hard, but also very brittle. Low ductility, low toughness. Think of glass versus plastic. Martensite is more like the glass. So you get this tiny zone, this hard spot that's incredibly hard, but has almost no give. It can't stretch or deform under stress like the metal around it. It just wants to crack.
Okay. So it's a weak point because it's too hard and brittle.
Precisely. If we connect this to the bigger picture, that hard spot isn't just a surface mark. It's a fundamental change in the material properties right there. It becomes a prime spot for a crack to start. Even under normal loads, maybe stresses the rest of the material handles fine, that brittle spot can fail. And things like residual stress or even hydrogen getting in there, delayed hydrogen cracking can make it even worse. A tiny flaw initiating a potentially huge failure.
That really paints a picture. But what about the other options? Stress razor sounds plausible too.
That's a great point, and where exam nuance comes in. Let's quickly look at why hard spot is the best answer here. Option A, it's a stress razor. Well, yes, the hard spot does act as a stress razor. Any sharp change does. But the reason it's such a severe stress razor and prone to cracking is the brittle nature of the hard spot itself. The hardness and brittleness is the fundamental problem caused by the arc strike. The stress raising is a consequence. So hard spot is more direct, more fundamental.
Okay, it's the root cause.
Exactly. Then C, lack of fusion. That's a totally different defect. That's about the weld not bonding properly to the base metal or previous layers. Critical flaw, yes, but not what an arc strike is. An arc strike is on the parent metal, usually outside the weld. Different mechanism.
Right, different location, different cause.
And D, it's a volumetric defect. Volumetric means things like porosity or slag inclusions defects that take up space within the weld. An arc strike is primarily a surface-subsurface metallurgical change. Yes, there might be a tiny crater, but the danger isn't the volume it takes up, it's the brittle material created.
So it's not like a hole or a piece of slag.
Correct. So this raises that important question. While stress concentration happens and lack of fusion and volumetric defects are bad, what is the direct, primary, dangerous consequence of an arc strike itself? It's the formation of that hard, brittle spot. That's the specific danger unique to arc strikes among these choices. Getting that distinction is vital.
That is crystal clear now. The visual flaw, the arc strike, it's just the tip of the iceberg. The real danger is the hidden metallurgical change, the hard spot, like seeing a tiny crack in a foundation. It hints at bigger problems. So what does this all mean for your next inspection or your exam? The big takeaway. Don't dismiss arc strikes as minor. They create brittle hard spots. That's critically serious. It can lead to cracking. Why care? Because understanding this, why not just the what, is what helps you pass that exam and, more importantly, become a really effective inspector who prevents failures.
Absolutely. And sometimes the most dangerous things look small. I recall a pipeline job. Several small arc strikes were noted, but maybe not given enough weight. Months later, under pressure, guess where the hydrogen cracks started? Right from those hard spots. A real-world lesson. Visual inspection needs that deep understanding behind it. Always ask why it's a problem.
A sobering reminder. Okay, that's a fantastic deep dive. It highlights looking beyond the surface. Thank you for joining us for this first session in our CSWP 3.1 exam prep series. Keep studying, keep asking why, and you'll nail it. We'll see you next time.